Welcome to the lecture on column design as part of the Structures by Design sequence, ARC 347 for fall 23. We're going to jump right into the columns. Last time we talked a little bit about the Maison Domino and Corbusier's idea that he had depicted here of, instead of having bearing walls on the outside and interior bearing walls, things that then define the space, that both these open slabs and the columns allowed for a new way of actually thinking about building space, spatial arrangement, even building expression, as now we see that the columns are replacing the bearing walls on the outside, which allows the outside to be now more wide open and expansive. Long before this, the sort of way of situating columns and column design had to do with either monumental architecture, in which they were looking at spaces which it was taller, bigger, more grand, looking at gigantic monolithic elements. And of course, these then define places where people would gather. And so you can see here Stonehenge and then the Temple of Karnak in Egypt. So the use of columns versus walls is what I'm trying to get you to consider here, and the idea that they could be a place to pass through, a place of ritual. Even then in ancient Greece, this idea of having it be a symbol not only of being able to lift up a temple and also having to be a place to gather, but that the elements of it were actual elements that showed a particular arrangement of culture and knowledge. So whether it's the Doric or the Ionic or the Corinthian, all of these things, seemingly have this sense of why that one element is there, whether it be the drum or whether it's the bass or the top Corinthian order. These are also then structural things, is what I wanted to point out. And so it has to do with either how the loads are transferred on top, how they're transferred in the bottom, even then the width or the entasis of the columns tries to allow for buckling. So again, as we've seen in other things, there's this combination of not just the intent of what the structural element is from a design perspective, but then the constraints that have to come through with construction and its technical behavior. I love this particular slide as it shows a sort of embodiment of the figure as a column. Helps us to then visualize how those forces would come through. Columns in their expression always still stick with this same question of both technical, structural, and expressiveness. And here, you see a column by Pierluigi Nervi. In this one, you can see that it looks quite different than the other columns I've shown. But the base of it here, the interior space of it, and the way it sort of has a foot that comes out in 4 different pieces, the way it uses ruled surfaces, it has a gigantic cap that comes up and all these sort of umbrella pieces that come out. All of this is still dealing with the same technical principles related to columns and how they work. It just has a very new expression of its materiality. Transitioning now to this idea of what columns are used for, and the idea of the column is that, of course, it's a way of allowing forces to work their way down and through the system. It's a sense of vertical continuity for load transfer. So we haven't talked much about this at this point, but one thing that columns or walls are useful for is the idea that they help establish a grid. So my idea here is that the structure then is going to help us to define the form, space, and the order, at least when it's done well. And you can see in red 2 very different types of systems here. One is a housing, one down here is a larger hangar. And so I'm defining the red load-bearing vertical transfer elements based on how it defines that space and volume. And in that, I'm able to draw a grid. By that, as the idea of what a grid could be, is you can have numerical and then alphabetical. So you start to have this center line that says, here is the order by which all the vertical load-bearing forces will be transferred. And on this axis is another control point for those, okay? And then down below, it's a very different type of a grid because it is a very different type of space. So then 1 and 2, and then A and B. The idea is that when you want to start laying something out, you draw that grid and you try to respect that grid. We don't like to then move where force transfer is going to be coming through. So the idea of here of dealing with the consequences is that what if this housing was up above and then this hangar was down below? Well, with the housing, you have all these walls that were then designed to be able to take on vertical weight. And as they take on their vertical weight, when they come down to the ground, they've got nowhere to go. Okay? So when we think about these grids and the alignment of these grids, you also want to think about that force transfer as it comes down. In particular, you see on the side here that would end up being quite problematic. So we have to think about the vertical continuity and then the load transfer of these. Consider the consequences then of what happens when those loads do come down, when we have columns that have them come down, and that doesn't continue all the way down into the foundation. It puts a great deal of load in the middle of this space. You can see it in the force arrows here. Column, 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 pushes down right in the middle of a span, and think about a gigantic point load coming in the middle of a larger span and what that would forces it would enact on that particular beam. There's a couple basics about the column design load path. As we know, as we've been going through for the last few lectures, we want to try to find the horizontal loads first. So we've been talking about how we would size the deck, and then the purlins and the girders, we would size those. Because these are pin connections, the load is transferred vertically. Thus, you can see the arrows that are straight up and down and up and down. So there's no bending moment. That means that when we diagram this, we have our uniform load, our reactions, our uniform load, reactions. Those reactions then, as we can diagram out, become the load that's transferred down. Eventually, all the loads from all of this thing are then accumulated into the vertical support elements. Because we've already dealt with sizing of beams, we're not going to go through this again. To quickly size the columns, we can assume that all of the horizontal spanning members, whether that's deck, purlins, girders, will be sized correctly. Okay? So if all you're really worried about is the columns, you can skip ahead by simply adding up all the anticipated loads that would be transferred to the column. This is, just like we did with beam design, called tributary area. In this particular diagram, I want you to look closely at it. It's trying to diagram the tributary areas for what would be transferred to each column. Now, in the corners, it goes half of the span, and then half of the span. So just that much tributary area goes to the corner column. Typical one back here, it takes half of this, half of that. So it takes all of this particular area. The center column, you can see, has twice as much area because it goes half this way, half that way, half this way, half that way. So the end columns usually have less tributary area than the center column in this layout. And then the smallest, of course, are the corners. In this particular one, I wanted to show what would happen if we didn't have a column in the middle. And in that, we'd have a much wider area of tributary area. So in this case, these columns here may have the most tributary area, therefore they may have the most load on them. Okay. Remember, as we went through and we talked about the loading that happens on these, both live and dead loads, that these columns then are going to have a lot of them in multi-story buildings are then going to carry multiple different types of loads. And so we want to think about these as an additive element. In each one of these tributary areas, it's the width times the length, and you would have the load from the roof. That comes down through a column. This one, live and dead loads of the floor, that doubles up this one. And then you have roof, third, and second, coming down into the foundation and then spread apart. So the question, something to consider when we talk about grids, is why are the columns drawn with the structural grid through the middle of the plan? When we go back and we look at how those actually lay out with a dashed line that runs through the middle or through the middle, whether that was A, B, C, 1, 2, 3. The reason we want to do that is the center of all the columns must align. Because not all of these columns have the same amount of force that they're resisting. This one has less, this has more, that has the most. And as we know, mass and area is related to how much force it actually has to resist. So one might imagine that the lowest column would be bigger than the highest column because it's in fact holding basically 3 times as much load. Well, how do we then make sure that those forces from the center of the top one align with the center of the second one and align with the center of the third one? We do that by then indicating it with the center line of the columns. A couple other design basics. We talked about this in the lecture of the shear, but the idea of punching shear. So when all those forces were accumulating in and around a column as they're going to transfer from the slab downward, again, we have a concentration of forces. Whenever we have a concentration of forces, we want to add more mass. In this, we're adding more mass as a column that comes up as a cap. In this case, a column comes up as one of the mushroom caps. It's just simply a way of spreading out the load at all the points to and from the column. So here's the diagram of what would happen if we did not, where the slab comes around, concentrated forces punches itself through. Interestingly then, as I mentioned earlier about even the oldest columns, they recognized that this force transfer between the top, where the stresses were consolidated, and the bottom, where then the stresses were consolidated and spread out, needed to have a different type of articulation in order to have it work structurally. And so the 3 parts of a column, the 3 typical parts of the column, the base, where it connects to a foundation, the shaft, and then the capital, where it connects to the top parts here. And so articulating those, not just from a decorative perspective, but then how those forces are being transferred, is an interesting way of keeping track of the idea that the stresses are then concentrated on the top and the bottom. Okay. So when you actually are thinking about what it takes to design a column, about the loads and the stresses that are within it, in order to size a column, we know that it's being compressed, right? So we have their axial stresses of compression. What else do we need to know? Like, for example, if all we need to know that is how much stress is under compression, then maybe we could just size a gigantic mile-high column, okay? How much weight can a solid 6-inch by 6-inch steel-high column? If we go back to some of the math that we had learned in a few semesters previous about the allowable compressive forces, we know the allowable compressive forces of a particular material equals the load divided by the area, or in our case, because we're trying to solve the area or the load, we can of course move these factors around. So load, material, area. And what to recognize here is, of course, it's spread across the entire cross section. So we apply this, and we'd say that, the fact that it's a mile high is irrelevant. That in fact, if we know that steel is 22,000 psi, that the area, cross-sectional area, is 36, we could put almost 800,000 pounds on top of it. And of course, we know that that doesn't seem right. We know that that column, if this is, of course, the Space Needle, we know there's no way that we could put that much weight on there and that the column would be okay. We know it wouldn't work that way because we know that a column isn't just sized about the compression forces that come down. We know that the issue is buckling. In fact, the only way to make this work would be if we would have areas in which it was stayed all the way around. So recognizing that the primary consideration of columns, that resisting the forces that come down, is actually relatively easy. It's resisting buckling that's difficult, and it's also difficult to predict. And the reason it's difficult to predict is that once failure in buckling starts happening, it can be catastrophic. So consider a weight up above, it's being placed on here, and if that weight pushes and the column moves to get out of the way, once that column moves to get out of the way, the only thing that's going to happen is this distance is just going to increase. The failure progresses rapidly, okay? This distance increases the more the column buckles to get out of the way. Therefore, catastrophic failure can happen relatively instantly just by buckling. So buckling then has to be our design factor. Sometimes this is very specific about the connections itself. This is showing you a column made out of precast concrete that has a hunch on the end, that has a precast beam, and then precast slabs on top of it. The center line from the load above is in fact going directly through the column, but the load from the beam, in order to have it connect into the column, actually rests down here. So its point, its reaction point is here. There is then this offset between where the center line is up above, where the beam load is coming down. Same thing actually happens then with a steel beam, center line, connection point there, okay? So this kern is what that's called. So placing a load anywhere within 1/3 of the column produces compressive stresses. Placing a load outside, produces tension on one side of the column as it goes to bend. We can handle that, but it's called eccentricity, and you need to sort of understand that that maybe starts some of the buckling, because this load pushing down doesn't have just straight uniform forces. What do you need to know about buckling? This is something that you probably already intuitively know, but it's worth considering here. The taller the column, these are the same column in terms of the cross-sectional area, the taller the column, the more easily it will buckle. Okay? So here I am pushing that, buckles easily, trying to push a 1/2 that size, and it takes much more force in order to make that buckle. Now, that's fine intuitively, but we kind of need to know how much weight it could hold before it buckled, right? And what are the factors are involved with why this buckled so easily and why this did not? You're not going to be asked actually to solve any of these equations related to Euler's formula here, but I wanted to show you one of the first mathematical ways of trying to come to terms with buckling, the critical buckling load on columns, because I think you'll find it interesting, especially as it relates to other factors that we've seen. P then is the critical buckling load. How much weight could it hold? And then the other factors should be familiar to you here. E, its materiality, the modulus of elasticity, in other words, how stiff it is, right? I, you remember also from the deflection formula, is the moment of inertia for the column's cross-section. In other words, its shape matters. And L is the effective length, how tall the column itself is. So you can see that the factor here that is the most influential, of course, is its length, or basically the height of the column itself, but that the material and also the cross-sectional shape matters too. To reiterate what we had mentioned earlier, this total load, in other words, how much could make it buckle, is based on the tributary area. So this is showing you then for a column, you would have a certain tributary area, and those increase, right? Each one of these would have a load per square foot. So that plus that, as it comes down and it comes down, that's how we then know how the loads accumulate downwards, and we'd be able to find the worst case scenario for how much load there is, and then be able to figure out whether that would buckle or not. So in order to find what this P, this load is, using Euler's formula, we can find the capacity for a 12-foot tall A36 steel column. From the charts based on a W16 by 40, we can find out its I value. Because it's steel, we could find out its modulus of elasticity, and its effective length then is 12 feet tall, so we can also then establish what that is. The maximum load, so I've identified the area where we'd have the maximum load, P, just substituting those other formulas, those other factors into the formula, would be 497,770. If the anticipated load on top of this is, say, 150 pounds per square foot, then the total area per column that this could be, working backwards, is if the maximum is in fact this 497,770, we divide that by 150 pounds per square feet, then this area, the area I have outlined in red here, could be a 57.6 foot by 57.6 foot area. Now that's of course getting us to the critical buckling load. We wouldn't want to get anywhere near that. We'd have to have factors of safety and things, but the theoretical idea behind Euler's equation is that in fact if we knew its material, its cross-sectional shape, the length and the height of the column itself, we could work backwards, find out that load. Once we know the load, then we can go back to the tributary area and find out essentially how big of a bay we can have. So how much, according to Euler, could we actually put on this mile-high column? 7.69 pounds, okay? Because again, we're looking at a mile-high column that we square. So that's not much weight. In fact, it doesn't even hold up its own weight for even probably more of a foot of it. So how much weight could it hold if we changed its effective length? If we, in fact, start to brace it, and in this case, I'm bracing it, say, every 1,000 feet. So if I start to brace it every 1,000 feet, remember what Euler's equation is telling us is its critical buckling load. Now that we've braced it, we've changed its length. Because we've changed its length, then that allows us to put more weight on it. So the very same column itself now can hold 214.4 pounds. Is this how we size columns? Nope. In fact, as you saw, there's really too much back and forth testing involved between one factor or another, right? Because we are also looking at like, well, how big is that potential tributary area? Then how do these factors do it? There's actually a more effective way to do it. So I wanted to show you these factors so that we can understand the back and forth or how those factors affected it. But before we look at this other effective way, what else do we need to know about the columns? So essentially, like Euler's formula, there's a couple things that we have to really consider here. There are 4 factors related to basic column design. 1, its material. Can it withstand compression? And how stiff is the material? In other words, its modulus of elasticity. Second, its shape. How is the actual cross-sectional shape, I, moment of inertia, help it be more resistant to buckling? The third part is its connections. How is it connected above and below? This, as we'll see, is a K factor, and this K factor starts to change its effective length of the behavior of the column. And finally, something called a slenderness ratio. The slenderness ratio takes into account the length and also the shape of the column itself. So, again, quickly coming back, columns resistant to buckling benefits from a bigger cross-sectional area, I, and a stiffer material. A shorter length thing, so buckling stiffness could be put in relationship to those factors. Let's talk through then the material aspect of column design and as it relates to this particular formula. Columns rarely rely on material's compressive strength alone. We look, in fact, its resistance to deflection. So its modulus of elasticity, in other words, its stiffness, is what we're concerned about. If we think about concrete or steel or timber, down below I've listed their allowable compressive stress, 6,000 psi, 50,000 psi, 1,150 psi. So if they're all loaded with the same amount and that column has the same height, you would see that these factors really start to come into play. You'd have a concrete column that would be 20 by 20, steel 14 by 90, timber 30 by 30. So they're, hugely different in terms of their size. The other aspect of it as relates to the shape. Are some shapes more resistant to buckling than others? Yes. So what we're trying to do with the shape is assessing its resistance based on its shape. We aren't really concerned about the overall cross-sectional area, but like beams, we're concerned with where that area is distributed. Moment of inertia, remember, was the way in which we could then measure where that area is distributed vis-a-vis its neutral axis point. This one's an important one to consider. In the diagram over here, I have 3 different columns. I have them in perspective and then in plan down below. I have a circular column, I have a tube column, and I have an I-beam. So all of these would behave differently in terms of their resistance to buckling, and that's what we want to get at here. Unlike beams, we cannot know which direction buckling is likely to begin, but if a column has a weak axis, it is more likely to buckle within that weak axis. Look at this one here. It's a tube that has area on far sides of that center point, but not much on the far sides of that. So if that was loaded down, it's much more likely, as this diagram to show, to buckle out and buckle out along those weak axis points. In the case of the I-beam, it's certainly spread its material out on this side and on that side too, but not much material further away from the neutral axis on the two other ends. So this one would be more likely to buckle on the two sides. When we select a moment of inertia, we must be conscious of asymmetrical shapes, like the tube, like the I-beam, that have weak axes. Second aspect of it relates to the shape. So to find a column's resistance to buckling, we use something that's known the radius of gyration. We define that radius of gyration r as r squared equals I, moment of inertia, divided by a, its area. What we're trying to get at here is I has to do with its shape, a, its area. We're trying to find where that area is located. So we're solving then for the radius of gyration. It essentially tells us how far away each fiber is on average from the neutral axis point. The higher the R value, the more resistant to buckling a particular shape is. Let's look at the steel manual again, and we see that for any particular given steel beam, they list an R value for its XX axis and its YY axis. So with its XX axis up here, this one has an R value of 15.7. That means it's pretty resistant to buckling. Okay, and this one is a 3.73, which means that it's not going to buckle in the top side. It'll be more likely to buckle in the side to side here. We'd have to use then the lower R value. So it's going to buckle to its weak axis. So if we took a W24 by 12, we found two different I values here of it. We found an I value in its X and an I value for its Y. And from the steel manual, we would know what its overall area is too. So its radius of gyration would be R squared equals this, right? We could solve for its R value that way. If we take a totally different one, a 12 by 12, we find out its controlling one because it's the lower of the two different moment of inertias, its area, its radius of gyration we solve as a 3.25. So it's more stout. If we take a circle, that has the same moment of inertia on either axis. Its overall area, go through the math, and that's a 4.4. So in other words, we have a 2.68 to a 3.25 to a 4.4. The higher the R value, the more resistant to buckling. This tells us what we intuitively know and what we covered in the last few slides. This one has its weight too far out on either side of that, which leaves it resistant to buckling in that orientation. This one, of course, is closer, more stout, has its material a little bit closer, but it's still resistant to buckling on that side, where the circular column has it equally distributed everywhere else and therefore is the highest resistance. I've made a little chart here to help you where it goes from low R to high R so that we can see the differences in what might make something a good to better to best column. If we have a solid tube, or if we have solid I-beam, these are first of all not symmetrical in terms of XX, YY. They have a weak axis and they have low I, meaning that they have a potential for buckling. If we get a little bit better and we start to consolidate these down so they don't have a weak axis, at least we've made them symmetrical. Now, unfortunately, in this one, it's super solid, so all the material is inside instead of on the perimeter because it's a solid piece. And this one, the sort of cruciform column, it still is pushing that area towards the inside instead of to the outside. Of course, it's still symmetrical, but it has a lower I because its shape is compact. If all we do is just simply take the material out of the middle, put it on the end, put it on the end, we have symmetrical high value shapes. So that's a very quick way of being able to understand whether something is going to be good in terms of a column for its cross-sectional shape or not. Biaxial symmetry in columns is something that we've understood for a very long time. I want you to think about, say, Gothic columns. And when we look at them, we know that the forces are coming down from those arches, and those forces are then being gathered by columns, and those columns take them down to the ground. And we also know that these buildings are very much dictated by the symmetry and the geometry of what's happening up above. But just in an abstract, what if we just cut off the column and took a look at it? Look at its cross section. It's solid because it's made of stone, but look how it's biaxially symmetrical. Look at how actually then there's no weak access to it. Then you start to think about and look at the columns in these cathedrals. And you start to see that, yes, even the biggest are biaxially symmetrical. We can see how the biggest ones then are taking on the most load. Therefore, they have the most area. You can actually see that these columns are resisting buckling to the outside. So they have their amount of area pushed to the direction in which they know that they're most likely to buckle. And the really beautiful part about it is when you start to be able to trace the loads, we can see these isostatic lines of both the slab down to the column. Gathering it, umbrella, down and in. Each one of these force lines then comes in and concentrates into a column. This column comes down, but of course, now that the weight itself is doubled, with these arches that are coming in, these arches that are coming in, the column itself gets bigger. This expression then of form, space, volume, and order is exactly why I started the lecture the way I did, is because I think that this is the important part of being able to see what the articulation of a slab and a column can actually give you in terms of being able to make a space more than just a way of resolving forces that come down. We talked about Pierre-Louis Dunervi's approach to this with the isostatic lines that went around, how those then came down into a column. So the third factor, besides its shape and material, is connections. This is kind of hard because we haven't gone through connections very explicitly, so I want to make sure and take a little bit of time with this slide. We have always assumed that things have pinned connections as it is now. If we choose different types of connections, whether those connections are fixed or whether they're hinged or whether they're free, it's going to change the behavior. Because all those different things are possible, whether something is braced or fixed or pinned for columns, that then changes how the column will behave. This factor is called a K factor. The K factor modifies how a column's going to behave across its length. First one, if it's fixed on both ends of a column, actually let me start with this, I'm sorry, I apologize. We're going to start with what we already know. A column is pinned on the top and a column is pinned on the bottom. In that one, it's going to behave like a beam, right? Where it's going to then pinned on top, pinned on bottom, it rotates freely. You can see the pin, how it bends. This column is going to behave as its actual length. What if we fix the bottom part? What if we put a moment connection here so it doesn't bend right at the end point? In fact, we see it has a bit of an inflection point here. That reduces the effective length of the column. This column went from one pin to the other. If we fix it, it actually is going to behave like a column that's a little bit shorter. If we fix the top and if we fix the bottom, this column actually behaves even shorter because each end then up, down, that column behaves even shorter than that. So meaning that this column, even though it is, say, 10 feet tall, because it's fixed, it actually behaves like a column that's 65% of that effective length. You can see this in any demonstration that you have. The other one I would show you here is the fixed and free end one. This seems weird, like why would there be a column that has a free end that doesn't hold something up? In this one, I would just ask you to consider stop signs, stop lights, other things like that that are structures that maybe aren't building structures that still would be fixed on one end and free on the other. And you'd see that they tend to move a lot and they buckle quite a bit. Pinned pinned, fixed median moment connection, fixed moment connection. We can see the double curve, fixed pinned, fixed free. So this one's floating. So these K factors are what we have to establish right off the bat. So again, here we are in the middle, pinned, pinned. That's going to behave at its actual height. So if this is a 10-foot column, it will behave like a 10-foot column. If we fix one end and we pin the other, and remember, pinning, we designate with a triangle, a circle. Fixed, just a flat piece there. This one's going to behave 80% of that. Fixed, 65% of that. If one end slides or one end is free, we rarely get into these on this side, but you can see that very quickly those are going to behave like a column twice as tall. You will be given these factors whenever you go to design a column. They will say the top part is fixed or the bottom side is pinned so that you can find this K factor. It tells you essentially, based on the connection, whether the column will act like a longer or a shorter column. So when it's fixed on the ends, it deflects less. Therefore, its effective length is what we're really after. So its effective length, this K factor, is always multiplied times its actual length. When you're working with structural engineers and you're working on a column, they will talk about the KL. The KL essentially means your column and how it's connected. Slenderness ratio is basically a check for compliance, just like it was with, this is our fourth factor, of course. Just like it was with deflection, it's a unitless ratio. It's basically trying to find out whether the column's effective length and its average width, it's KL divided by R being its radius of gyration, can define its particular slenderness. A short column would have a KL over R under 50. An intermediate one would have a KL over R between 50 and 200, and a long column would be over 200. Let's take a look. This short column has a KL of R under 50. You might think of it like a wood column. Intermediate, this is where most of them are going to be, usually is a good R ratio that's in there. And then a long column, we know that it has a very long, very tall, usually a low R, and there's a high risk of buckling with that. So we've gone through all the four major factors: material, shape, slenderness, and connections. Depending on what's given in the formula, as this says, you may be able just to use a chart to find a properly sized column. And in a lot of cases, in fact, this is what you're going to be given. Okay, you'll be given a load, the column length, and K, the end conditions. The nice part is we really don't have to do much math. Once we do that, we can look at handbooks or charts to find an acceptable condition based on either its R, radius of gyration, or P, its load. Column design charts are there just like there are beam charts. In this one, they will show you a nominal size of what the column itself is. In this case, it's for wooden, southern pine, Douglas fir column sizes. In this, you can see on top, the top factor is the effective unsupported length, it's KL, with respect to its least radius of gyration. In other words, it sorted it for you. What do we see here? Height, right? Because this is about its unsupported length. So is it 6 feet, 8, 10, 12, etc.? Then it's also sorted by weight. Column size, allowable load, which is its weight, effective length, KL. Quick example to show you how this would work. Design a column in A36 steel for this situation, 130 kips, it's fixed on one end, it's pinned on the other, it is a 20-foot height. So first, identify all those factors that are in there. Okay, so that means right away, fixed and pinned. Does it matter whether it's fixed on the bottom or fixed on the one side? Nope. All you have to know is that whether it's fixed on one end and pinned on the other, So in this case, it's fixed on the bottom and pinned on the top. Does that really matter? No, it doesn't matter at all, because the column, again, is still going to behave in a similar way in terms of its effective length. So it's fixed on one end, pinned on the other. Its K factor is going to be 0.8. So the actual effective length of a 20-foot column, because it is fixed, is going to be 20 feet times its 0.8, or 16 feet. It's able to resist buckling like a 16-foot tall column, even though it's 20 feet long. In other words, it benefits from being fixed. We also know P, the load acting on it, is 130 kips. So now all we have to do is look for a chart to find out what type of column size would support this load. It's this easy. We find its 16-foot effective length. We come down here. These are in kips. So 1, you find its height. 2, you find its allowable load. 3, you project over, and you find the allowable size. So we selected a W8 by 35. It shows us the effective length, and it can support that amount. So that's it. Well, we should probably check to make sure this isn't going to fail from compression too. So we have another quick check of its allowable load, its allowable compressive forces, the load, and the area. We run a quick check, and we figure out that actually it could resist twice the actual load that's on it. You rarely ever have to actually go through double checking its compression, because frankly, these columns are not going to give you an allowable force if this cross-sectional area wouldn't be able to resist it. I mostly wanted to do that just so you can see that's the factor. So you have a column, tributary area, that adds up as you go down. So when we have multi-story buildings, all these then accumulate. We have to do for the worst case scenario, meaning at the very, very bottom, because this would have the roof, fifth, fourth, etc. Often then the ground floor of a building will be taller also than others. Maybe it's got a lobby or other things like that. So in other words, it's the worst case in terms of load, and oftentimes it's the worst case in terms of height. So designing columns is often just as simple as finding that tributary area, adding it up as we go down. So again, we dimension to the center line of the columns so that we can make sure that knowing as that load adds up as we go down, each one of these columns gets a little bit bigger, that they all align up. Can we do this? Can we design then a column, an A36 column, this one here, across the roof, third, second, first? In this, I'm giving you 150 pounds per square foot for the total load, 75 pounds per square foot for the roof, because the roof is lighter. The column bay size is a 30 by 30, and the columns are fixed at all joints. I'm going to take this out of its context of the larger building, simply look at this on its own. So the first thing I need to look at is, because it was fixed on both ends, its practical length, its K factor, is 0.65. So here I've drawn it just on its own. I'm going to start at the roof. The actual height was 15 feet. I take it times its K factor. I get 9.75 feet. So you can see it really acts like a much shorter column. I'm going to round up to 10 feet because it's got to be the worst case scenario. The total load that was given was 75 pounds per square feet. The tributary area that was given was 30 by 30, therefore 67,500 pounds. Go to the chart, 10-foot tributary area, 67, move over. That column is a W6 by 16. Next one down, we have to add in the roof load, which we just found, plus the tributary area times its load factor. This column then also is fixed on both ends, so we know its height. This one has 202,500. So again, 10-foot height, 202. We find that, comes across. That's an 8 by 40. We can do this for the next one down and the next one down itself. We find out that when we get to the very bottom, that actually we have a W14 or a W12 by 96 that's available. So that's one way that you could quickly go from the top, down, 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 just by adding up all of these factors. So on your worst case, the ground floor, it was 25. It's fixed on both ends, so it actually rounds up to 17. And we know that we would then be able to add up the load from the roof, second, third, etc. So the overall cumulative load down here it has to resist is 472,000. And again, we come down to its height, it's effective, and both of these down here then would allow you to say, there, maybe that's all I need to know is what's the bottom column. In this example that's also from the book readings, the other thing I wanted to point out here is that it's a similar process, right? You got a roof load with a tributary area that comes down into this particular column. In this one, what I wanted to show you is these aren't two columns. It's one column. Its total length does go from the foundation up to the roof, but because it is braced by the intermediate floor, its effective length is there and there. With that then, we'd be able to choose a column area, check the stress, our unbraced length factor, because it's fixed on one end and pinned on the other, we'd be able to find our KL. We would round up as needed from the KL. We would go to the column chart as we looked at, and then based on the KL, its connection and its length, and the P, the load that we've established through the floor loads, roof loads, etc., and then we'd check that slenderness ratio. In that case, we'd be able to look at scenario A and scenario B, different lengths. So we'd be able to go from A1 is scenario A, which was a 12-foot column, pinned on both ends, so 12 foot, pinned on both ends. It's supporting 100,000 pounds, just over 100,000, so we can't use this, so we go to A2. That comes across and we have, these options then. Scenario B was a 12-foot column with fixed ends. If we then fix the ends, our allowable height is, or effective length is less, which puts us here. We move over right away. So the difference between those two factors, just by changing whether it's fixed or whether it's pinned, you can see the difference in the size of those steel columns. Just like with better beams, there are better shapes. Long columns have to be designed with a combination of compression and bending, so they behave, at least in part, as beams. And this helps us to realize that because they're behaving like beams, we want to be able to put our material where the stresses are. So in addition to cross-sectional area, longitudinal shape is also a factor. In this, we have some basic column, which is just fixed top to bottom. We had a concern about punching shear. So if we had a concern about punching shear, as we even saw in historic columns, we're able to add more sectional area to that. So you could add more sectional area by spreading out that load. The other thing we know about how columns are going to behave is that there's moment stresses, especially if these are fixed on the top and bottom. There's a high moment stress down here, there's a high moment stress down here. Just like with beams when they have a moment fixed connection, we can spread that out. The analogy then being with a body of legs that are spread and arms that are spread. In other words, if it's fixed on the top and bottom, and these are moment connections, we could actually have an optimized form in which it's wider on the bottom where there's a moment force, it's wider on the top where we both have punching shear and a moment force, and it narrows where we don't have those moment stresses. This still has a weak axis. It could still buckle front and back. So why don't we just take that same idea on the other axis as well? And what we get is an optimized two-way column. We can really start to think about these optimized columns and the shapes of these columns and how they actually fit with our other slab design work. If you start to think about how you can optimize a slab and the location of where forces are distributed within the slab, and then how that column works too. So again, I have wider at the base, wider at the top, stable feet, a buckling resistant form because it's biaxially symmetrical. But this is also a viable option too, right? In this one, now I have This is fixed and fixed on the top and bottom. So this is exactly like we just looked at here. Fixed, fixed. And because I don't want it to buckle front or back, I have these feet that come out, these feet that come out. I've got the arms that come out, the arms that come out. Because I'm worried about punching shear, maybe instead of having a skylight above, maybe I have it solid here, and I run skylights in between, and run skylights in between. Look at how that is just essentially a loading diagram. That's just our diagram of the tributary area. But it's so much more than just a diagram of tributary area because it's an actual space with light and air. This idea that you can articulate these columns to have light that maybe comes in where your tributary area spreads apart at the capital. It's such a common way of expressing this thing. So you have the airport in Barcelona. It's the Clemson School of Art and Architecture. This is Eero Saarinen's Miller House in Columbus, Indiana. Right? Another train station, Denver Airport. This is in Brazil. Gaudí Sagrada Familia. You have this really interesting idea of being able to spread out all of its tributary area load by making essentially a gigantic column that comes around here. It's St. John's in Minnesota. And here again is the front part of the same Clemson School of Art and Architecture where, again, the concern here may have been buckling, and so they reduced it by having V-shaped area.